Welcome back. We are options are expensive and require capital. Can modern technologies ranging from automation and digital technologies like big data and analytics be leveraged to lower the heat rate by lowering the fuel costs and improving the power plant efficiency? We joining us this evening. We thank you for your time. So please go ahead and speak about how you can improve efficiencies in power plants.
Well, thank you very much for your nice introductory words. I hope that you're all doing fine, that you all stay safe in India during this COVID period. We have managed quite well this year, and hopefully we'll be all heading to better times. Let me introduce my theme to you today. I will quickly share my screen with you. Hold on. Okay. Two. Okay, let me just quickly share this. So you hopefully can all see my presentation now. It would be nice if you could just give me a couple of signs over the screen, then I know that I'm on the right page.
We cannot see your presentation yet.
You cannot see my presentation. Hold on. Okay, hold on. Was it the wrong screen? Can you see it now? Can you see my screen now?
No.
Hold on.
You have to click on share screen.
Share screen.
And then you have to click on the share button on the bottom right.
Yes, I have. And I share my screen too. I allow to use it. And then, can you see it now? It worked yesterday.
Yes, so. Yes, it's working.
You can see it? Okay. So, yes, let me say a few words about our company. I know that quite a few people in India know our company already because we have been working together with people like NTPC, also other power companies to optimize their measurements. And today I'm going to talk about how to improve boiler efficiency and lower heat rate. Our company has been around for about 25 years, and this is just a brief overview over the projects that we have been doing so far worldwide. As you can see, we are not only active in the field of power station, but we're also active in the field of steel plant optimization and cement plant optimization. All of these are quite energy intensive industries, and the potential for optimization is very large. Now, of course, one big focus for us has always been coal-fired boilers, and coal-fired boilers give you a vast opportunity to lower emissions in absolute terms, quite big numbers. You can save 10,000s of tons of CO2 per annum on each boiler. The regions where we are active in boilers are actually from the beginning to the outlet. Let's start on the left-hand side of this picture. You can see the side view of a large steam generator. And let's start on the mill. And this is also going to be the main focus of my presentation today, measuring pulverized fuel flow in boilers to each burner, a very important and pivotal part to optimize heat rate on a boiler. Now, associated with that, you should never forget, of course, measuring the primary airflow to the mill, which is equally important. I will not focus in too much today on that subject, but it is a very important matter. Let me come up with a provocative thesis. I believe that in 90% of the boilers on this planet, the airflow measurement is wrong. It's not correct because it's drifting. So that's a big issue that needs to be addressed as well, but not today. But we're doing that. Along with that, we're also measuring secondary air. So the combustion air in the boiler that helps you to combust your coal. The secondary air measurement, along with the coal flow measurement, are the most important measures to get your stoichiometry as low as possible. You want to use as little gas flow as possible to oxidize your fuel. And this is what I'm going to talk about today. Beyond that, we also have solutions to measure airflow in burners. We have measurement systems to measure flue gas. Quite interesting, flue gas flow. Very often you have a non-symmetrical flue gas through the precipitators and the ID fans. Left and right side air heaters have different flue gas flows. And also the unburned carbon in the fly ash, a measurement system that we have installed in quite a few stations in India already, and of course in hundreds of applications around the world. And last but not least, total flue gas flow measurement on the stack. This might become a very important measurement in the future once that a global CO2 trading kicks in. Plants will have to measure their emissions quite accurately. Today, let's focus in on pulverized fuel flow because that's really the biggest leverage that you have in order to optimize your boiler. This picture should be quite known to everybody who is in coal combustion. The combustion parameters. For example, you can see CO, O2, NOx, but you can also see the overall efficiency. And when you look at this picture, you can see that there are two zones in which boilers are usually operated in. The comfort zone, which is actually a zone of fairly high oxygen level. When you have a high oxygen level, you can make sure that you have fairly complete combustion, which usually goes along with a low loss on ignition or a low unburned carbon, which is good for you. But of course, it also goes hand in hand with a high O2 loss, a dry gas loss, which is fairly high, and a high NOx, right? So what people like to do is they like to reduce the air to fuel ratio to lower values. And by that, reduce the excess air, increase heat rate, reduce heat rate, increase efficiency, and also reduce the NOx. And that gets you to the optimum zone. The big problem is that on each burner, this diagram is you're not at the same point in this diagram on every burner. On every burner, you might be slightly different. On some burner, you might be substoichiometric, so you already can see your CO and your LOI come up. And on another burner, you might be still in the comfort zone and burn too fuel lean and too oxygen rich. So what I'm going to talk about today is the burner to burner optimization of your combustion in order to get every burner into this optimum zone that will help you to run your boiler at the highest possible boiler efficiency. The key tool for this is a measurement to measure the pulverized fuel in each coal pipe. Now, our company has invented a unique system that can measure the coal velocity, the coal mass flow, as well as coal deposits and the consistency of fuel flow in your pipes. And I will explain to you in this short session why this is so important. It is not only important that you have the same coal mass flow in average on a burner by burner level or on a burner by burner basis, but it's also important that the coal transport is very uniform, that you don't have pulsations. Yeah, the air gets into your burner very consistent, but the coal flow very often pulsates, and that means you will see a very big fluctuation in CO, NOx, and other constituents in your flame. You want to get that as consistent as possible, and that has to do a lot with coal transport between mill and burner. And the system that we have developed can optimize, can look at that and give you an optimum picture of what you have in your burner, in your coal pipe. The system that we have developed is basically a microwave resonance system. And this microwave resonance system allows you to have a look in some short section of your coal pipe. And what we see in that short section is the ratio between coal powder or pulverized coal particles and carrier transport gas, which is primary air. So we can see how much coal dust you have in the pipe and how much air you have in the pipe. The airflow we measure with a correlation technology in order to measure the velocity. So we know how fast is the air traveling in your coal pipe. And this velocity of airflow is very similar to the velocity of your coal. But what we also measure is the concentration of coal. And this can be very different from pipe to pipe. You can have pipes with very high coal concentration. You can have pipes with very low coal concentration. And that is a very important thing, because this also determines of how you can control the coal mass flow. You don't control coal mass flow with changing the primary air or the air velocity. You control coal mass flow by changing the coal density, the coal concentration in your pipe. And I will show you this. But at first, let's look at how the concentration measurement works. We use this pipe section as a resonator, and we excite this resonator with a sweep of microwave frequencies. You can see on the bottom of this picture. So you get a typical resonance curve with this typical Gaussian shape. Now, when you put some coal dust into this pipe, you would see that this curve is starting to shift. This right-hand side curve is when the pipe is empty, and the left-hand side curve is when the pipe is loaded with coal. And the frequency shift of that curve is a direct proportional indication of how much coal you have in the pipe, how much coal concentration. And if we multiply that with our cross-correlation velocity measurement, we get coal mass flow. This is in a nutshell how we measure. I will be happy to take more questions on that and go into the theory of it. It's a very elaborate and very interesting field of high frequency measurement. But for now, I would only leave it at that point. We can have a very sensitive measurement of coal concentration in your pipe and coal velocity. And what this also can measure is the coal deposit that is in your pipe on horizontal sections, which is a very big indicator of transport stability of your coal. And I will talk about that in a minute. How does the system perform? You can measure absolute coal mass flow and air to coal ratio to each coal pipeline. You can measure flow velocity. You can measure everything by an accuracy of about plus minus 5%. You can detect deposit and coal transport problems. The mounting of this is quite simple. I will show you some pictures. It's a drill and tap sensor that you put into the pipe. And we have installed these systems around the world. How does the system look like? You can see here a typical setup. On the left-hand side is the big main panel. This main panel can measure several mills. So you can have 4 mills, 6 mills that all run into this panel. On each mill, you have a so-called LFB, a local field box. This local field box measures the individual pipes of each mill. And then you have the sensors that go into the pipe individually, including a temperature sensor and the cables. And then what we call the reflector rods, which go into the pipe before and after our measurement sensor to create that resonator space that we are measuring. Here you can see a typical arrangement. That's a wall-fired unit. The whole thing, of course, also works for tangentially fired units. In this example, we have measurement locations in horizontal pipes as well as in vertical pipes. Here you can see the typical arrangement of sensors on each pipe. On the side, you can see the sensors that are drilled and tapped into the pipe. Or here you can see even a better picture on a horizontal. You can see that for each sensor, all you have to do is drill a hole into the pipe, cut a gear into the pipe or a thread, and then you just screw the sensor in. That's all you have to do. It's a very simple installation that you can perform. Now, before I go on to optimization, we have to talk about a very basic problem that you all have. If you're running a mill and on your mill outlet, the coal distribution is not uniform, so you have one pipe carrying more coal than the other pipe. The question I pose to you is, how do you correct for that? How can you achieve to get the same coal mass flow into each pipe? And for this, I've given you a schematic picture of a typical mill outlet. You have the outlet pipe on top of a hole, basically, that's in the top section of the mill. Now you have this PF rope or these PF flying in the turret that goes out on the mill exit, and it flies more or less in a spin. It comes right out of the classifier, and the classifier gives the airflow a spin. So it's spinning around, and while it's doing that, it's hitting one outlet and then goes into the outlet pipe. What do you do if you have a large rope, so an area of high coal concentration that hits a pipe? In this case, your coal concentration in that pipe is much bigger than in all the other pipes. And this is something that you cannot correct once the coal is in the pipe. Yeah? If the coal is in the pipe, yeah. Or if you don't have enough coal concentration in your pipe, you can turn these deflector plates so that the coal enters into your pipe. This mechanism that you can see here on a typical turret, this mechanism has proven to be very effective in controlling coal concentration in your pipe. And please note, controlling the coal concentration is the only way that you can move coal from one pipe to another. There is no other way. If you have a variable orifice in your pipe, you will only control the primary airflow. But you will not, which is also important, but the main part comes from controlling the coal concentration. Here is how this looks in real life. You have your deflector plates. You can see on the right-hand picture how they were installed on the mill top. Here you can see how the insertion was done by cutting out a piece, putting in an adapter plate. All these adapter pieces were delivered by our company, so we can actually give you the complete design and engineering for your specific mill. And this is how it looks then once it's installed. So what do you do with this device? Basically, what you can do with this device is getting your mills from this concentration distribution to that, right? So from a complete difference in coal mass flow, you can equalize the coal mass flow to a very good level. Or let me show you this in a typical picture of measurement graph that we have measured on a 6-pipe mill. The picture on top shows the coal distribution before, and the lower picture shows the coal distribution after. I have not shown here a picture of the attemperation water in the superheater, but usually that's a very impressive thing. If you have superheater attemperation flows, in many boilers, these attemperation water flows are not the same. You have a higher flow on one side and a lower flow on the other side. This shows you that your heat in the boiler is not distributed uniformly, and that heat distribution problems originates from your burners. You have burners that give more heat into the boiler than others. And as soon as you fix this imbalance, you can see that your temperation water flow gets in line. And that is a very big indication that the fuel distribution in your furnace has become far better. So that in itself is a big advantage already, because you're having a better heat distribution now in the boiler. And that means that the overall average back-end temperature on your boiler outlet will go down slightly, because you have a better use of heat transfer in your boiler, as if you had a big heat imbalance. If you have a big heat imbalance, you're not using the heat from the flue gas ideally. And remember, all these little changes, a few percent here, a few percent there, have a huge effect on coal consumption and on ID fan and FD fan power consumption. These are the big savings you get. But there's another thing that you can do. If you have a better fuel distribution on your burners, on a burner by burner level, remember the graph I showed you in the beginning with the CO and the O2. If you do that, you can do the following. On the left-hand picture, you can see the stoichiometry. So you can see that some burners are high in excess air and others are lower in excess air. If you start to reduce the overall O2 on such a situation, you can see on the lower left-hand picture, you will see that some burners will start to go into the reducing atmosphere. You will have high CO, high unburned carbon, right? This is also true if you're running over fire air. If you're having a two-staged combustion, then of course your burners are always running on a very low stoichiometry, but they have to run in a very narrow window. They have to run in 0.8 or 0.82. And if you have burners that are far bigger or higher in coal flow, you will have many burners running out of specification. Some burners will run high and produce NOx, and someone will run low and produce CO and unburned carbon. So you will have to run a slightly higher O2 or a higher overfire air in order to burn down the CO, in order to keep the unburned carbon under control. And remember, only a few burners can spoil your combustion. You have seen in this first picture that the CO goes exponentially. So a slow substoichiometry will create a large CO spike. Yeah. You can reduce sometimes CO by a factor of 10 if you get the combustion stoichiometry correct. So this is very important. Now just imagine you could have the same stoichiometry on every burner, which is the right-hand picture. So all the burners were in the right area. Now you can reduce your O2 slightly to get the whole thing into the optimum combustion zone. Yeah. What am I talking about here? I'm talking about boiler outlet O2 being 2.5% and you can get it down to 2.3. Or you have a boiler outlet O2 of 2.8, you can get it down to 2.4. Or some boiler, you can get it down to 2.1 or 2.2. These are big changes. These are big changes in your boiler efficiency. We are talking about 0.3, 0.4% efficiency gain on dry gas loss. And we're talking about the same efficiency gain again on fan power. You can have efficiency gains of 0.6, 0.8, 0.9% boiler efficiency. Now, this is a big number when you convert it to dollars. Here you can see also that we're having a big impact on NOx. I know that many of your boilers are compliant now with the new regulations, but if you have a boiler that uses ammonia, whether it's an SCR or an SNCR, increasing boiler efficiency will always move your NOx values in the right direction. Which means if you have an SCR, you will use less ammonia with an optimized boiler than before. The ammonia reduction, especially in India, ammonia prices are high. You pay a lot of money for ammonia. The ammonia reduction is another big saving. If you don't have an SCR or SNCR, you will only increase your performance on NOx. Now, one thing I would like to explain to you, which is very important, is not only the coal mass flow split to each burner is important, but also the consistency of the coal transport. When you have coal transport velocities that are too low, the coal starts to settle in horizontal pipes. Why is that a problem? It is a problem because the coal pipes now starts to become a storage of coal. So the coal stores in and stores out. So the burner gets a fluctuation of coal, and that again gives you a stoichiometry which is not constant, but which keeps on bouncing up and down into the high NOx and the high CO region. Yeah. Let me show you this, how this looks like. This is a brand new boiler that we have measured. It's a T-fired boiler in Europe. And you can see that one pipe, this pink pipe, pipe number 4, gives you a very spiky concentration measurement. Yeah. On the lower picture, you can see the associated velocities. And we now have increased the velocity on the mills, the primary air velocity, slightly, just to see what happens. Now, what does happen is that if you increase velocity just a little bit, the spiking completely stops. You have a very clean flow indication. And if you decrease velocities again, the spiking is back. So what can you do with this tool? You now can find out the minimum velocity that you need in order to keep a good coal flow transport. Believe me, I've seen many plants in this world, also in India. I've seen plants where the paint has come off the coal pipes. I know that many of these coal pipes very often have fire in them. You have pulsating flows, especially when you have long horizontal runs, for example, on T-fire units. And this is some problem that really spoils your effort to get a better combustion efficiency. Because if the fuel is not going into the burner consistently, you are running into problems. You could even run into blockages. This is a typical picture that we have seen in one plant where people did not believe us that they have a blockage, but in the next outage, they saw that they have a catastrophic blockage. And what these blockages cause is also flame shootbacks, which is a safety hazard and can also happen. So this is a very short way of how we optimize the coal transport, the coal distribution in order to reach a lower stoichiometry. The other thing that is on the horizon also in India is the use of renewable energy. The use of renewable energy puts many coal-fired power stations into the problem that they have to get bigger load swings. You have to be able to jump up and down in load and really complement the fluctuation of the renewable energy. Our measurement has been deployed successfully in various European power stations, even now in a biomass fired power station, to have a much better control of the mill outlet. When you have a mill and you change your swing on load changes, you can see on the upper left-hand side picture, big load swings when you make changes. Now, when you use the Promicon measurement and a state controller to optimize mill control, on the lower right-hand picture, you can see how you can achieve very smooth load jumps with our measurement technology. And the way we do that is that we introduce a new state variable, which is basically the coal mass flow out of the mill, measured by Promicon. And this allows the control system to make faster adjustments to load changes, which have an overall positive effect on mill output, on feed water pump synchronization, on boiler stress, yeah, and also on the consistency of the boiler master steam generation. This is basically, in a nutshell, what we can do to optimize the boiler, lower heat rate, at the same time increase boiler flexibility, and also help you with your NOx. Last but not least, we have a lot of references around the world. I'll be happy to talk to you about projects that we have done, about clients that have worked with us to optimize their boiler. The combustion optimization is a very tricky thing. And the most important thing that you need for that is a proper measurement of the combustion fuel that goes into your boiler instantaneously. So this is the key to make your boiler better in efficiency and lower your heat rate. Thank you very much. I'll be very happy to take any questions.
Right. Thank you so much for your presentation. We are getting a few questions on the live chat, but there's a request to all the participants to raise your. Is this different from variable orifice mechanism? Perhaps a deflector is used over the mill in all coal pipes, or only one which makes the flow in
yes,
all
it is.
coal pipes?
Okay, you're breaking up a little bit, but I hope that you can hear me. The question is absolutely correct. This is very much different from a variable orifice. And the difference is that the variable orifice changes the pressure drop of the overall pipe. And the variable orifice changes the gas flow as well as the solid. But very often this means the solid concentration will go up and the gas flow velocity will go down, so that the mass flow of coal will not change substantially. Our pedal sensor is inside the classifier outlet, and it prevents too much coal from getting into a pipe. And this coal is then being deflected to the next pipe. So what we really control is the coal concentration. We're not controlling the velocity, we're controlling the coal concentration, and this is much more effective in changing fuel flow to each burner.
Right. We have one more question. Okay, so there is a question. Does the coal pipe deflector affect the coal particle size going into the burner apart from the coal classifier? This question is coming from Ashutosh Peshkar.
Yes, and a very knowledgeable question. Of course, when you have these deflector plates, yeah, it looks a little bit like the classifier blades. We have not found the major impact that we see, if you don't have the deflector plate and you sample the coal out of each line, you will find that the pipe with the biggest coal concentration also has the disproportionate highest amount of coarse particles. So our deflector plates have an influence on the particle size, namely that they level out the particle size distribution, right? We don't change particle size in total because we are sitting after the classifier. The coal that comes by our pedals will always end up in the pipes. So no coal is rejected by our pedals. So there is no way that we can influence the overall classification. But these pedals have the tendency to spread out the particle size more evenly to the pipes. So they will level out the coal mass flow, and they will also level out the coal particle size distribution, which both helps you with loss on ignition and unburned carbon.
Right. We have Mr. Subodh Nigam, who wants to ask you a question.
Mm-hmm.
Mr. Nigam, please go ahead, ask your question.
Yes, sir. Actually, I want to know what is the mechanism of online adjustment of deflectors, and is there any measurement required before adjusting these deflectors?
No. What we are doing is our system has, as I explained, we have this resonator, and the change in resonance frequency is proportional to the amount of coal concentration. Yeah. So let's say you have 4 pipes on all 4 pipes, we are measuring the same delta frequency with our system. In this case, we know the coal concentration in each pipe is the same. So in this case, no change is necessary. However, if our system sees a difference, then you have a high difference in coal concentration. Now, when we see that, and when you also see a difference in, for example, a temperation water or O2 on your boiler outlet, you have more than enough evidence that the fuel and air distribution in your boiler is not uniform. If you're then adjusting the deflector plates so that our indication of coal flow becomes more even, you will always see that the temperation water imbalance also gets better. The O2 gets better. So the overall combustion parameters will go in the right direction. Now, of course, you only have 2 or 3 temperation water measurements. You only have 2 O2 measurements, but you might have 20 or 30 burners. So you have to measure the burners and to adjust the burners in order to get these parameters correct. So that's usually the succession of events. We first measure the coal mass flow. We make a corrective action with the deflector plates, and then we can see the improvement in the overall combustion.
Right. We don't have any more questions. And thank you so much for answering all the questions that you have. Thank you so much, Mr. Conrad, for coming in today and sharing with us your presentation on the efficiencies that can be brought in. I think Mr. Khatri also wants to say a few words.
Mm-hmm.
Khatri, we can't hear you. Okay, are you on mute? I think there was some connectivity issue where we couldn't connect with Mr. Khatri. We'll just give him another chance to come on again and say a few words. Khatri, please go ahead. Okay, I think till the time Mr. Khatri comes in, let's take in one more question, which is coming in from Mr. Sankule. Mr. Sankule, go ahead, ask your question.
So my question is, between the 2 following options, which one is desirable? The first option is to keep CO within limit and increase O2 up to 5.2%, or second one is to keep O2 2.5% limit and increase CO up to higher side.
Oh, you asking me which one is better?
Sorry? Which one is better?
Okay, that's a very good question. Look, these are non-linear things. Let me share my screen again and show you the associated. Can you see my screen?
No.
Oh. Can you see it now?
I can see you, but not your screen.
Okay. Let me share the screen again.
No, sir. Still not.
Can see now?
Not, sir.
Okay, then I just explain with words. You have, on one end, you have the O2 loss going up and up and up. And this is what happens if you increase your O2 more and more and more, right? Yeah. When you do that, the CO goes to nil. There will be no CO. The CO is gone, right? But you will have a big loss on your dry gas and also on your fan power. Because remember, your fan power increases by the third power with flow. So now you're trying to pull back. You're trying to pull back the excess air, because excess air means loss. You have a high heat rate. You want to lower the heat rate.
Okay.
You can do that to a certain limit, but then you will see the CO will come up exponentially. So you get better and better and better in efficiency, and to a certain point where it tips off, and then you are losing so much efficiency. And this maximum point, this is the point where you want to be. This is the best way to run your boiler. Now, what many people understand is that you have this graph for every boiler. But the reality is you have this graph for every burner. And you might already have some burners which are producing lots of CO, while other burners are still too high on O2. So the first thing you want to do, you want to get all the burners to the same stoichiometry. So now you can all sing from the same hymn sheet. Do we want to be higher or lower in O2? And if all the burners are the same, then you can go to that maximum point of optimum combustion where you have the lowest loss. So you have no big CO and no loss on ignition with the lowest possible O2. That's where you want to be. And that's the high art of running these monster boilers on the best spot. And this is where you save lots of money. And when you do that, you will also be in the right direction in terms of NOx. Then your NOx will also be okay.
Right. Mr. Conrads, I think another question from Ashutosh Peshkar has come in. He's saying, does the variation in coal density in different coal pipe affect the coal air mixture velocity measurement in the coal pipe?
No, it does not. It does not influence our coal air. I mean, we measure the coal density, right? So we are measuring the coal concentration in each coal pipe, and if the coal concentration is different, then of course your fuel to air ratio is also different. It's the same thing, yeah. And that's a very good point here, yeah. Many people do a lot of effort in the power stations to get the fuel to air ratio correct in the mill. Yeah, the fuel to air ratio in your pulverizer must be something 0.48 or point whatever. Yeah, so you have a very clear mixture of how much fuel you need, how much air. It's in your mill handbook. Now, this fuel to air ratio is also very important for your combustion on your burner. Your burner is designed for a certain primary air to fuel ratio. Now, what we see is that after the mill, sometimes you have burners with 30% higher concentration than others. And that means that your fuel to air ratio in each burner is completely different. And that means all the design of your burner and the mill makes no sense if the flows are not correct. These are only working correct if your flows are correct. So therefore, you have to try to get this problem right. It's a big problem.
Right. Thank you so much, Mr. Conrads, for joining us this evening. We've taken up all the questions from our participants, and thank you so much for answering them. If there are any more unanswered questions, I'm sure they'll get in touch with your team and get some of those answers on a one-on-one basis. I think there's another one last question. Okay, no.
Okay.
Everybody's appreciating this session. Thank you so much, Mr. Conrads, for joining us on the conference to reduce net heat rate for TPPs 2021. It has been an insightful and a valuable session for our participants. Thank you so much for joining us.
Thank you for having me. I always enjoy. Very, very nice. Thank you very much.
Thank you. So that wraps up day one of the Reducing Net Heat Rate for Thermal Power Plants virtual conference. We hope you've enjoyed the sessions and picked up some valuable insights for your company's operations to optimize clean energy usage and to, of course, increase the efficiency of your plants. Please join us again tomorrow at 10 a.m. sharp for more knowledge sharing through panel discussions and presentation sessions. And do remember to sign up for the Fly Ash Utilization Summit that we are having in April in Goa. Do reach out to have a look at the brochure, and do sign up, because as Mr. Khatri explained earlier in the day, the seats are limited and you want to be there because you want to gain the knowledge and the information that will help your business. Thank you for joining us, and we'll see you tomorrow.